Welcome to this session. This session is about single replacement reactions of the net Ionic AP formatted variety. I remind you that this will be question 4 in the free response, and it'll be the first question that you face right after they have snatched the calculator from your grasp. And they're actually the one thing that we can practice all year long, so we should. We should do them as often as possible. You should have quizzes on them weekly just to make sure that you stay in condition, because it is like being a conditioned athlete. So my name is Renee McCormick. I'm with the National Math and Science Initiative, and I think we're becoming good friends by now. So my Texas twang aside, let's get started. Single replacement reactions are where one element is going to displace another in a compound. That's just classic textbook definition. So in this case, one element is oxidized and another is reduced. Now, I remind you that elements in their standard state have oxidation states of 0. So you'll see me write that in this upper corner or above, perhaps. But a lot of times on element, I write it in the upper corner and then above on these things. So that would have to be plus minus of the same variety. So active metals replace less active metals or hydrogen from their compounds in aqueous solution. So if you use an activity series, which is simply a reduction potential table, to determine the activity, the more easily oxidized metal replaces the less easily oxidized metal. That means the metal with the most negative reduction potential will be the most active. So don't confuse that with what we do in electrochem when we're trying to put together a galvanic cell. We use the most positive reduction potential to be reduced to an element. In this case, we're talking about an element actually bumping something else out. So, like in our first example, magnesium is going to react with a solution of iron 3 chloride, and so we want to write the net ionic equation for that. Well, since silver, mercury, or lead is not present between magnesium or iron, we can get rid of that as a spectator and simply focus on the fact that turnings is a word that means solid. Chances are you've never been in a machine shop. Have you ever been in a machine shop where people work metal and fashion them into car parts and cogs and wheels and things that go into big giant machines and such? They shave metals down, and those shavings come off as little curly-Q corkscrew looking things called turnings. So that's a code for solid, and if it's solid, then its oxidation state is 0. And with the iron, this Roman numeral is being kind to you and telling you that was iron 3, so its oxidation state is +3. One exception to that is mercury 2. Mercury Roman numeral 2. Oh, that's Mercury Roman numeral 1. That's where I'm headed. Sorry about that. Mercury Roman numeral 2, since I goofed up, I'll go ahead and do it too, as well. There's Mercury Roman numeral 2. No surprise there. This is the surprise. Mercury Roman numeral 1 is diatomic as it exists in this ionic form, and the diatomic ion, the polyatomic ion that's diatomic for mercury, has a 2+ charge, meaning each one of those mercuries is a +1 itself, hence the +1 or the Roman numeral 1 in these parentheses. Okay, so just be on the lookout for that one and only exception to the Roman numeral thing. The other thing you should also recall is that silver, cadmium, and zinc do not have Roman numerals, because you should just know their charges. They don't make a lot of different oxidation states. So if you put them in alphabetical order by symbol, A, C, and Z, the first one's a +1 and the other two are both +2. Silver, cadmium, and zinc. All right, so magnesium makes the only ion it knows how to make based on its position in the periodic table. It is a 2A metal, so these will make +1s. You've seen me do this before, but it's worth, I think, repeating. That column makes +1s. This column makes +2s. These are those transition metals that can make a plethora of different charges, and we use the Roman numerals. But silver, cadmium, and zinc, this one makes a +1. Pen in this program doesn't work as well. You get the idea. And this would make a +2. Both of these would make +2. I give up. I can't make my pen work well. Okay, so that means that iron is going to be reduced either to iron 2+, which would be another correct answer, because as long as it's reduced, we're okay, but they took it all the way to the metal, to iron metal. Sodium is added to water. Anytime you add an alkali metal, which is this first row over here, to water, they're going to make the hydroxide of the metal and some hydrogen gas. And so when you put these metals into water, it's quite a spectacular reaction. Big Fools on YouTube, I think you can find lots of different videos of people throwing bits of sodium into ponds and lakes and streams and such, and running like the wind away from it, because it's not good. It's not smart. These also liberate a whole lot of heat. That hydrogen gas that's going to be made can actually go kaboom. So you're going to hear me say kaboom a lot because of this hydrogen gas right here that's being formed. So take the 1A metal, toss it into water. You're going to make the 1A ion and the OH minus hydroxide ion, which makes it basic, and another word for basic is alkaline. So they're called the alkali metals, and their neighbors next door in the 2As, these folks right here, are called the alkaline earth metals and do sort of the same thing. So active nonmetals replace less active nonmetals, and the cool thing, again, about the periodic table is this is the activity series for the halogens. Fluorine is the most reactive, chlorine is next, bromine next, iodine last. So chlorine gas, that means I write Cl2, is bubbled into a solution of potassium, 1A metal, as an ion spectator, iodide. So halogen plus halide yields halogen plus halide. They basically, one replaces the other in terms of the activity series, and so this was sitting here at neutral. This had a -1 charge. So that's going to create iron, I'm sorry, not iron, just did iron, iodine, I2, plus the chloride ion. Then we're always going to be on the lookout for some tricky redox reactions that appear to be ordinary single replacement reactions. Hydrogen reacts with hot metallic oxide to produce the elemental metal and water. So that would look like this sort of an example. Hydrogen gas is passed over hot copper 2 oxide. So here's your hydrogen gas. Here is your copper 2 oxide. What are you going to do? This element is going to bump that copper 2 out of there, and this is going to leave us with the element copper, and then the hydrogen is going to come and pair up with its good buddy oxide to make water. So a metal sulfide reacts with oxygen to produce metallic oxide and sulfur dioxide. These are the things you have to work at memorizing a bit. Chlorine gas reacts with dilute sodium hydroxide to produce sodium hypochlorite and sodium chloride in water. Copper reacts with concentrated sulfuric acid to produce copper 2 sulfate, sulfur dioxide, and water. Copper reacts with dilute nitric acid to produce copper 2 nitrate, nitrogen monoxide, and water. And then copper reacts with concentrated nitric to produce copper 2 nitrate, nitrogen dioxide, and water. 1, 2, 3, 4, 5 things you just kind of need to memorize. So you may want to take these 3 as a set, since they're all about copper, and just kind of figure out what's going on with each one of those so that it makes it just a little bit easier for you to memorize. Now, in terms of how copper actually reacts, you really should go to the wiki page, the AP Chemistry, which is most likely how you found this video in the first place, nimsy.wikispaces.com site, and look at the Ira Remsen video. That'll help you get a little bit better grip on that. Okay, there's not a lot to do here, but just kind of dive in. So again, we're always going to be on the lookout for words that mean pure solids and liquids, and we're going to be on the lookout for spectators. So one must know one's solubility rules. That has not changed. You can go back and review them. You should have them in a handout from the wiki page, or from your teacher, or from your book, or from the internet. In other words, no excuses. You need to know your solubility rules. So a piece, that implies a solid, of aluminum, so I have a single aluminum element, so it's going to bump somebody out of a compound, is going to react with a solution of silver nitrate. Nitrate is a spectator in this case. It's almost always a spectator. And so here we go. So one metal was an element. You don't have to put the 0. I do it for emphasis to remind you over and over again its oxidation state is 0, and it is an element. So the thing that was an element will become an ion, Aluminum only makes one kind, and that's a 3+ ion. And the other will go to become an element. In other words, somebody was oxidized and somebody was reduced. All right, so now we're forced to balance this. Here's the scoop. You got to decide how you want to do this. You can do this with half reaction method. It's just going to take you longer. Or you can be a little smarter than that. You can think about, let's do this with charge. So total charge on the left, +1. Total charge on the right, +3. If I triple this, I get +3 on each side, which forces a tripling there. And I have not unbalanced this by atom. So I'm balanced. Or you can go ahead and figure out that what you would slash off in these two half reactions would be 3 electrons. I'm going to do one just to humor you so you know what I'm talking about. If you've learned redox, if you have not, there's a separate video on that, not only net ionically, but back in chapter, what is traditionally 4. And so there's a whole balancing redox by half reaction method sort of video that I did. So go back and review that if you have no idea what I'm talking about. So who's going to be reduced? That would be Ag+, because it has +1 oxidation state going to Ag0. Who's going to be oxidized? That's going to be aluminum at 0, going up in number to Al3+, +3 electrons, plus an electron. And so if I'm going to add these together, I would have to triple everything up here, because the goal of this game is to cross off and slash off those 3 electrons, in which case you get exactly what I got. So you can do it this way, it's just going to take you longer, or you can embrace the idea about charge on both sides and just kind of think it through. It's really not as painful as it sounds, that thinking thing. Aluminum metal, okay, they gave me a hint, we're just talking about this, is added to a solution of copper 2 chloride. No silver, no mercury, no lead, so this is a spectator. Cu2+. Again, somebody was a metal. I call these easy greasy redox. So that's going to become Al3+ again, because it's the only thing it makes. And Cu2+ could go down to Cu1. You could do that. I'm going to take it all the way to the metal, but either one is correct, whichever way you want to do it. So I got 2 on the left for a total charge, 3 on the right for a total charge. Gotta go to 6. So I'm going to need 3 of that and 3 of that. I'm going to need 2 of that and 2 of that. 6 on the left, 6 on the right. We're good. And I'm through balancing. But again, if you don't get that, then you can do the half reaction. Okay, so if you have not paused me and been doing these one at a time by yourself, shame on you. It does not do you any good at all to just sit here and watch this video, because watch me work these, because you know what? I know how to do it. I want you to know how to do it. So pause me now if you haven't already done so, and you work number 3. Then when you have tried it, then you can come back and listen. But that's the way this needs to work. All right, you're back. Hydrogen gas, so I don't have to think about that. Just write H2 in its elemental state, is passed over hot copper 2 oxide. Well, oxides are generally insoluble, so that's not going to be ions. That's going to be Cu with a 2+ charge, so it needs 1 O. Well, this is a classic single replacement. We're going to have H2O as the hydrogen comes and bumps copper out of position. It's like stealing somebody's girlfriend. And now poor copper doesn't have a date for homecoming. So, is that balanced? By golly, it's balanced. Know when to quit. Small chunks, another word for solid. Ooh, of solid, even better. Sodium plus H2O. Foolish endeavor. Foolish, foolish endeavor. First thing that's going to happen is kaboom, but the sodium is going to dance around on the surface of the water as it reacts very violently, and it's going to generate hydrogen gas, which is the kaboom part. I like to write it at the end, for instance, for emphasis. I want you to think kaboom in like a Roadrunner Wile E. Coyote kind of way. And then sodium sits here with these 1A's in the alkali metals, so alkali, alkali, alkali means make some sodium hydroxide, which is a strong base, which is going to dissociate immediately into Na plus and OH minus. And now I have some balancing to do. Because I'm not balanced by atom, so if I double this and double this, I get 2 O's on each side, 4 H's total now, and 1 sodium. However, my charges do not balance. Why not? Because I have 0 on the left, 2 minuses, and only 1 plus on the right. So if I do this and this, now I have a balanced equation. So if there is enough heat, which this is a very exothermic reaction, if there's enough heat, then this hydrogen gas that is made will explode. It'll go up into flames, just like the Hindenburg did. Bad design, that whole idea of H2. Seemed like a good idea at the time. Helium, not so flammable, much better concept. All right, so number 5. Calcium metal. Again, that implies just plain old calcium with a 0 oxidation state. You don't have to put that. I just do it for emphasis. Is added to a dilute solution of hydrochloric acid. So this chloric part is just a spectator since silver, mercury, nor lead is present. So just think of this as H+. So calcium plus H+ is going to yield Ca2+. It's going to dissolve the metal. In other words, add acid onto the metal dissolves. It ionizes, goes into the calcium 2+ ion, plus H2. So to balance this, clearly I'm going to need 2 of those. And I think I have it. I have 1 calcium on each side, 2 hydrogens on each side, and the charge balances, 2+ on the left, 2+ on the right. Again with the magnesium turnings. Turnings being a word for solid, so just Mg, oxidation state of 0. Again, there's no silver, mercury, or lead present, so we're going to add this to iron 3. So somebody's oxidized and somebody's reduced, so the only thing that magnesium can do is make a 2+, but iron could do that. Another correct answer, didn't finish that one off before I went to the next one, sorry about that, is this. So it's just a matter of which one do you care to balance. So if I balance the top one, what am I going to do? I've got 2s and 3s, so it's a 2-3 trick, that's all. See, that's why I don't like the top one. The top one takes me longer. I'm going to ditch the top one. You can do it, but it's easier if you look at this 2 and this 3 and say, okay, I want 2 of the 3s and 3 of the 2s, and then just match up your elements because it doesn't mess up your charge. And now I've got +6 on both sides. If I do it the other way, I get into a little bit more of a tangle. So that's kind of the technique I'm trying to teach you, is to go for the simple answer. There's more than one correct answer in a lot of these cases, so go for the simple one, the one that occurs to you fastest. Chlorine gas, so I don't have to think too hard about that, just Cl2, is bubbled into a solution of sodium bromide. That's a spectator, so it's just Br-. So we're back to the classic halogen, halide. What was a halogen becomes a halide. What was a halide becomes a halogen. And then we need to balance. And we are now balanced by charge. And we're now finished with that. A strip of magnesium implies solid is added to a solution of silver nitrate. Spectator. What was a metal becomes an ion. What was an ion becomes a metal. What was a metal becomes an ion. What was an ion becomes a metal. Now then, I have an imbalance of charge, so what am I going to do about that? Well, let's try doubling this, and I'll at least get my 2+. If I double that, that doesn't change the charges. I got 2+ on both sides, 2 silvers on both sides, I'm golden. Again, you can do it with the half reaction method. Just going to take you a little longer. I'll beat you in a race. Solid, well, that's pretty straightforward. Calcium, so Ca, no charge. Again, you don't have to put the zeros. I just like doing it. It makes me happy. H2O. Okay, so this is an alkaline earth metal, but alkaline still being the key word. What's going to happen here? We're still going to make the hydroxide of the metal, this 2A metal, and it's calcium. We only have issues with these 2 little guys at the top. All of these 2A and 1A metals make strong bases, which means we completely dissociate or ionize them. So be on the lookout for beryllium or magnesium, but we're into calcium. The truth is you could write calcium together or you could write it apart. It's kind of on the border. It depends on whose book you're using. I always write it apart, but if you wrote it together, you didn't get a wrong answer. They'll give you credit for it. So it's on the fence, is what I always say when it comes to solubility. All right, so now let the balancing games begin. What have I got going on? I got 2 H's, I got 3 H's. If I double this, I can get to 4. If I double that, I get 2 O's in the bargain, and I have 4 H's on both sides. And I, more importantly, have 0 oxidation, 0 charge on the left, And the 2 plus of calcium is canceled by 2 minus hydroxides. So we're balanced, and we're good. Liquid bromine, Br2, is added to a solution of potassium iodide. Potassium is a spectator. Iodide. Looks familiar. A, halogen, halide, halogen, halide. Halogen becomes halide. Halide becomes halogen. Balance the equation. 2 and 2. And it's balanced by atom, and it's balanced by charge. Do a happy dance. Take your points. Run. Move on to the next question. Chlorine gas is bubbled into a solution of potassium iodide. Looks remarkably familiar. Halogen becomes halide. Halide becomes halogen. 2 of these, minus 2 on each side. Balanced. Check. Move on. Lead foil implies solid, immersed in silver nitrate. What's going to happen with this one? Got to contemplate that. Nitrate. Oh, nitrates are always soluble. Don't have to contemplate that. We have metal plus ion. What was a metal becomes an ion. You can make it 2 plus or you can make it 4 plus. They both exist and they're both equally correct. I'll do this one down here. And then what we do know is that silver can only be a +1, and so it's only going to go down to the metal. So let's balance these. They're balanced by atom, but they're not balanced by charge. But if you double that and you double that, you have that one balanced. Again, they're balanced by atom on this bottom one, but they're not balanced by charge. So I'd need 4 there and 4 there. I've got to balance it by both ways. So you choose either one, equally correct. I know it bugs you that there's not just one right answer. Solid zinc strips. Solid strips, either one implies zinc metal. Added to a solution of copper 2 sulfate. Sulfates are soluble except silver, mercury, lead, and barium, strontium, calcium. I always have to look at the periodic table because I know it's those 3 right there. So copper 2 ion. So what was a metal becomes an ion. What was an ion becomes a metal. And we have 2 plus on each side, so we don't even have to balance anything. Yippee, yippee, skippy. And then another sodium metal. I wish they'd have used a different one. This is going to work for any lithium, sodium, potassium. It gets more exciting as you go down as well, because the valence electrons are where all the chemistry really happens. And so as you layer more and more layers of energy levels onto these nuclei, and you get these electrons farther and farther from the mother nucleus, they become less tightly held and more ready to react. And that just means you must run ever so much faster if you're fool enough to even attempt this, which I do not recommend. Do not try that at home. Watch other idiots on YouTube. Alright, so sodium metal is added to water. Easy enough. So they're called the what? What's that family name again? Alkali metals. So we're going to make sodium hydroxide, and you're asking yourself, is that strong or weak? Well, it's a 1A metal, so they're all strong. So dissociate it. And the kaboom comes from the hydrogen gas and the vast quantity of heat that is given off. So we need to balance this. What do we do? If I do this and I do this, I get 4 H's on both sides and 2 O's on both sides. And that should... No, that does not do it because I'm not balanced by charge. 0 on the left, a -1 total on the right. But if I do that, I can get 0 over there, and I can do that. No harm, no foul in terms of charge change, and we're good. A bar of zinc metal implies a solid, is immersed in a solution of copper 2 sulfate. Again, neither copper nor zinc are the 6 elements that are insoluble with sulfate when ionized. So Cu2+. So what was a metal doesn't stay a metal, becomes an ion. And what was an ion becomes a metal, or at least it becomes reduced. So you again could go to copper 1+ if you wanted. and just balance your equation correctly, and it's fine. But my equation is balanced, so I don't even have to worry about it. I'd get that point automatically. And finally, oh look, yet again, do you think this is important? Pick a 1A metal and put it into water and learn that reaction. So Na plus H2O, alkali earth metal, is going to make Na plus OH minus, dissociated because it's what? Strong. Plus hydrogen gas. Enough heat present? Kaboom. All right. That is it for single replacement practice. And now it's just a matter of you practicing over and over again. There is absolutely no shame whatsoever into reworking this set over and over again until you start to get them right. You have to decide when you want to start making excellent grades on these quizzes. It's totally up to you. Polyatomic ions must be memorized. Solubility rules must be memorized. Practice, practice, practice. And I've also told you before, there is a website that you can go to where you can practice this. And this is the website right here on my page. You can pause. You can write it down. You too can go out there, and when you're getting ready to take a quiz, you can get it to give you one kind, like we've been doing, to kind of get us started, or you can get it to do a mishmash and mix a bunch of them together. It is in the new format, so it will ask you the descriptive question, and it will not give you bunches and bunches to choose from. It will just give you 3. And you'll have to deal with those 3 and only those 3, and then answer the little, and balance them and all that junk, and then answer the little descriptive question at the end. All right? So, thanks for listening. I hope you find this useful.